Okay, this lecture is going to be about time series modeling. We've already gone through time series analysis, which I think gave you some idea of how you would approach breaking down a time series into its component parts, right? We talked about signal and noise and autocorrelation and stuff like that, non-stationarity, and approaches for assessing sort of the behavior and underlying characteristics of time series. And now we're going to talk about how to, once you understand some of those characteristics, to replicate them in synthetic data, right? So to come up with a time series or a simulation of what wind generation or electricity demand could be in the future, based on what you know about the underlying statistics and time series characteristics of that data in the past. So there's a couple different applications of time series modeling. And the first is more similar to time series analysis that we've already talked about, and that is just to further your understanding of the underlying forces and structure that produce the observed data, whether that's wind data or price data or electricity demand data, etc. The second one is a little more active and goal-oriented. So, if you're trying to understand the underlying characteristics of data, usually that's because you want to either model the system for an undetermined amount of time, just to understand how it might interact with other types of time series, or the decision making at a power plant or at the grid level. You might also want to be able to forecast or even predict values in the future based on time series modeling. And so there's, as you can imagine, a pretty wide array of applications for this, and that can be it can be used in financial markets. It can be used for forecasting all sorts of different things, whether it's weather or economic variables for electric power utilities, etc. And so I think this is a pretty transferable part of this class. Time series modeling, if you get into it, can be useful in a lot of different areas. So through our discussion of time series analysis, we went through the different components of a time series, or the words we use to describe different components of time series. And one of the ways we talked about that is sort of breaking things up into signal and noise, right? So the signal is the stronger patterns and trends that we are looking for, that we would pull out of a time series. And we tend to think of signals as being more important, and they're sort of the object of desire in terms of what we want to understand about a time series. But understanding the noise can also be important, especially the relationship between signal and noise, and understanding, making sure that changes in the underlying process are attributable to the signal as opposed to the noise, and sometimes that can be kind of confusing. We also talked about autocorrelation, so that's memory in a system. We talked about periodicity or seasonality, long-term trends, and we used the word stationary versus non-stationary to talk about long-term trends. And that doesn't just mean gradual increases or decrease in the average or the mean of the process. It can also mean average or long-term changes in the standard deviation or variance around that mean. And we also talked about noise, right? And we talked about white noise, which is just sort of like putting your hand into a hat and drawing out a random number from a standard normal distribution. But we also talked about how noise itself can be autocorrelated, right? So you can have noise that's distributed around this zero mean process, but the value in one time period might help determine the value in other time periods. So we made the distinction between true white noise, which is just reaching your hand into a hat and grabbing a number from a normal distribution, versus other types of autocorrelated noise. The type of model we're going to really focus on today that's able to replicate autocorrelation in time series processes is called an autoregressive, or AR model. So this is the basic structure of an autoregressive model. And YT here this is the process that we're trying to model. That's the value we're trying to predict or forecast. And it's a function of time. So YT is the value of Y in time period T. And you can see that we're assuming here that YT is we can predict using these other variables on the right hand side of the equal sign. And you see some coefficients, the B's, and you can also see that we're assuming here that the value of Y in period T depends directly on the value of Y in period T minus 1, so the period right before, plus this WT, which is white noise, right? So that's a random number from a standard normal distribution. So there's just a random element to this process as well. And we describe the order of this autoregressive model or the lag even, is the number of immediately preceding values in the series that are used to predict the value at the present time. So in the case of this equation, this is a first order, or lag 1 autoregression, because we're assuming directly that the value of Y in period T only depends on the value of Y in the period right before, but it doesn't depend on the value of Y in period T minus 2 or T minus 3. And the nomenclature here, we describe an autoregressive model with a lag 1 as an AR1. If the lag was 2, we would describe it as an AR2 model. And here's an example of a second order autoregressive model. So same general structure. We're wanting to predict the value of the variable Y in period T, and this time we're saying that it's a function of not only the value of Y the year before, or the period before, in T minus 1, but also the value of Y 2 periods ago in T minus 2. And we have an extra B coefficient here that corresponds to the weight or the importance of the value of the process Y in period T minus 2, and then we also have this white noise variable at the end, right? So that's just a random selection from a normal distribution. And so we call this a second order autoregression. We write it as an AR2 model. And so you can sort of get the hang of this here. More generally, if we were talking about a K order autoregression with K lags, we would write it as an AR parentheses K. And so that is a multiple linear regression in which the value of the series at any time t is a linear function of the values at times t minus 1, t minus 2, and t minus k. And so remember, just now I referred to this as a linear regression, right? And so the structure of this should sort of remind you of this multivariate regression. Remember, in MATLAB we were using the MV regress, right? In the structure of that, we were saying we have a dependent variable, y, that's based on the linear combination of a bunch of independent variables like x1 or x2 or x3 or x4, etc. In this case, we're saying that a process, y, is sort of a linear combination of itself, but in previous time periods. And so we would fit the coefficients b here basically the same way we would via fitting any sort of multiple linear regression or multivariate regression. So here's a key question. we know we may be able to see visually by plotting the autocorrelation function of a time series that there's memory in the system, that it's autocorrelated, which means the value of the process in one period depends on the value in previous time periods. But how do we quantify how much memory is in the system, right? How do we know what order to choose for the autoregressive model? In other words, how do we know how many time periods we should account for when trying to predict the value of a process in the next time period? And so remember from our discussion of autocorrelation, I don't know if that's from lecture 14, it might be 13, I actually think it's 13, I moved the numbers around a little bit. This is the equation for the autocorrelation function, right? This looks sort of like the equation for the correlation between any two variables, but here we're really taking the correlation between a series of measurements and measurements that are of that same process separated in time by a certain number of lags k. And remember the output of this, if we have we can calculate the correlation of a time series with itself shifted at any number of lags. We can plot those correlations on the y-axis here as a function of lag, right? And so what this plot is showing is that as you shift a time series progressively one period at a time, the correlation between that shifted time series and the original time series declines. And it's really high at first, which basically means there's high memory in the system. The value at any given time period is very closely related to the time period or the value of the time period before. But that starts to decay over time. So a related measure to the autocorrelation function is a time series partial autocorrelation function. And so this is the partial autocorrelation at any given lag or time shift k is the autocorrelation between the original time series yt and the shifted time series yt minus k that is not accounted for by lags 1 through k minus 1. And I know that's sort of a tricky thing to wrap your head around, but hopefully it makes sense that if you're talking about an autocorrelated time series with a lot of memory in it, the correlation between yt and yt minus k is influenced by the correlation at lags less than k, right? So between yt and yt minus 1 and yt and yt minus 2, etc., all of those sort of influence the autocorrelation between yt and yt minus k. And the partial autocorrelation function is a way of removing those intermediary effects and just isolating the portion of the lag between yt and yt minus k. So the partial autocorrelation function is mostly useful for our purposes in identifying the correct order or lag of an autoregressive model. And so in theory, the partial autocorrelation of any sort of autoregressive process should be 0 at any lag that's k plus 1 and greater, right? Because we're only accounting for the correlation between the time series and lag k, and we're removing all other significant autocorrelation. So at any sort of lag greater than k plus 1, sort of by definition, we're assuming that the partial autocorrelation function would be 0. And so if the autocorrelation plot, and if we're looking at a time series and we plot the autocorrelation function, and it shows some significant memory in the system, then the first thing that we do is take the sample partial autocorrelation in order to identify the order if we're going to try to put a model together. And so here's an example here of Google price data, and clearly there's autocorrelation here, right? This is a process that has quite a bit of memory in it. When it's high, it stays high for a while. When it's low, it stays low for a while. And so this is a scatter plot of the original time series and the time series, the same time series shifted by one period, right? So we're plotting on the y-axis or the x-axis, sort of like x or yt minus 1 through the end of the time series minus 1, and then on the y-axis or the y variable here is the original time series. So just as a point of reference, if we were doing a scatter plot of a time series in itself, this would be a perfectly diagonal line, right? Because if we're just doing a scatter plot of a vector of a particular time series we're interested in, and then we're doing a scatter plot of that time series with itself, that's just a diagonal line. So you can see this isn't a perfect diagonal line, but it's pretty close, right? There's some error around this this perfect diagonal line. But what that tells you is that at lag 1, this Google price data, if you did a scatter plot of the price data with itself shifted by one period, you would have a really, really high linear correlation, which suggests to you that the value of the Google price data, if today related to what it was, yesterday, is very, very high, right? Those are very highly dependent on each other statistically. So this gives you a visual idea of the difference between the autocorrelation function and the partial autocorrelation function. So on the left hand side we see the autocorrelation function, and you can see that it persists, right? Like the autocorrelation in this series persists way out to several different lags here. The right plot here is of the partial autocorrelation function, and we're identifying here in the partial autocorrelation function that the value of the partial autocorrelation really drops off to insignificant levels past lag 1, and so as a result, what we would identify here is that an AR1 model is most appropriate for this Google price data. So another approach for modeling univariate time series is a moving average model. And so a moving average term in a time series model is different than an autoregressive term, because an autoregressive term is basically saying that the value of some underlying process y in period t is a function of previous values of y in period t minus 1 or t minus 2, etc. The moving average term is sort of assuming something similar for the white noise variables, the errors, right? And so the structure looks kind of similar. So we have this underlying process yt that we're trying to model, and we have some sort of fixed mean, mu here, and the value of yt or y in any period t is the function of that mean, plus a random noise component yt. But we're also adding here now this other variable yt minus 1, right? And so what that means is that we're including some memory in this in the errors, right, in the random component of the time series that's driven by sampling from this white noise variable, we're assuming that there is some persistence in those variables as well. So the value of y in period t is a function of not only what you're pulling out of that hat, that normal distribution wt this period, but also what you got the period before. And similarly, when we talk about moving average models, we describe them with an order or a number of lags that we're considering. And so the order for a moving average model, similar to an AR model, is how many previous time periods of worth of information we're including in the model when we're trying to predict or forecast what the value of the process is going to be in period t. So a second order moving average model, an MA2 model, has an extra term at the end, and in each case here the theta variables are coefficients similar to the B coefficients we had in the autoaggressive model. But now you can see for the MA2 model we have 2 periods worth of previous residual or error information that we're incorporating into what the value of y is in period t. And more generally, you can write the equation for a moving average model as an MAQ, where Q is the Q order of this model, and you can go out as many lags as you want. So there's some general properties of a time series with a moving average 1 model. The mean would just be the expected value of yt over time. And so if we're assuming a constant mean here, then at least in terms of that statistical moment, we would have to describe this as a stationary process, right? So we're not going to see long-term shifts in the mean. You can have values above and below, but we would generally consider it to be what we would call mean reverting. So eventually it would hover around this mean, going up and down above it. The variance associated with the underlying white noise process is the variance of yt. And we can describe its autocorrelation function using this equation as well. So note that the only non-zero value in the theoretical autocorrelation function for a first-order moving average model is for a lag 1. At all other autocorrelations, at all other lags, autocorrelation is 0. And so the autocorrelation function with a significant autocorrelation only at lag 1 is thus an indicator of an MA1 model, right? Likewise, if you plotted the autocorrelation function and you had significant autocorrelation at lag 1 and 2, that would suggest a possible MA2 model. So here's an example of the moving average model. So let's assume we have a first order moving average model, which means we're predicting the value of this process y in period t as a function of its mean, which we're saying its long-term mean is 10, and innovations of this white noise variable wt, which we describe as a standard normal distribution with mean equals 0 and variance equals to 1. And we have this first coefficient theta that describes the importance of whatever the random noise was in the previous period. That theta value is 0.7. And that means that we can calculate, based on the equation I showed on the previous slide, the theoretical autocorrelation function is 0.7 over 1 plus 0.7 squared. And that gives you 0.4698. And the autocorrelation is equal to 0 for any sort of lag greater than or equal to 2. And so we can plot that theoretical autocorrelation function for the moving average 1 process, and that's what this plot shows at the bottom. In practice, a time series sample that we're using won't actually provide such a clear autocorrelation pattern. If we're talking about a time series that has moving average qualities to it. And to demonstrate that, we can take that same model that we just came up with. We have this underlying model that we're saying the value of y in any period t is equal to the long-term mean, 10, plus a random innovation of a white noise variable, wt, where wt is you're randomly sampling from a standard normal distribution, plus 0.7 times the previous innovation, the innovation of the white noise variable in the previous time period. And so if we can create a random sample of this by just, what we're randomly sampling here is from the standard normal distribution, and we're retaining information every time we take a new sample of what that noise variable was for the previous time period. And so that we're simulating 100 values from this model with sort of, we're using a Monte Carlo simulation from the white noise variable. And that's what this figure at the bottom shows. And so this is sample data. Right now we can't tell that much from the plot. But given the sample, we can then plot the autocorrelation function. And so we would use that using the autocor function in MATLAB. And so if we plot the autocorrelation function for our randomly our simulated data, that we simulated 100 different values of this model with the model structure that we specified before, and then we can calculate the autocorrelation function just for that sample. And you can see it looks quite similar to the theoretical autocorrelation function that we could calculate. So there's a really, really big spike at lag 1, and then it doesn't drop to 0 because you can see there is some minor autocorrelation that persists out to 10 lags here. But it is within the bounds of statistically significant autocorrelation, which is marked by these blue dotted lines. And so this is pretty close to the theoretical information that we thought we would get when generating random samples from this model. So the other interesting thing that this points out is, if you recall, we used the partial autocorrelation function to identify the correct order or number of lags for an autoregressive model, but we use the autocorrelation function to get the correct number of lags to account for with a moving average model. So there are a number of other classes of models that sort of combine autoregressive and moving average models, and one of those ARIMA models. So the AR here stands for autoregressive, the I stands for integrated, and MA stands for moving average. These are also called Box-Jenkins models, and these are models that may possibly include any combination of autoregressive terms, moving average terms, but also differencing operations. And remember, differencing is when you're you're simulating a process that's really based on subtracting or understanding period-to-period change in an underlying time series. And so when a model only involves autoregressive terms, we call it an AR model. When a model only involves moving average terms, it's a MA model. When no differencing is involved, the abbreviation ARMA is used. So that's a model that has autoregressive terms and moving average terms. And in most software programs, the elements in the model are specified in the order AR, and then differencing, and then MA. So in other words, a model with only two AR terms, but no differencing and no moving average terms would be a 2-0-0 model. A moving average model with an order of 2 would be specified as a 0-0-2 model, and a model with one AR term, one first difference, and then a moving average term would have the order 1-1-1. So we've talked a little bit about how to match autoregressive modeling with time series by identifying the order using the partial autocorrelation function. And we do something similar when we're trying to attribute a certain type of moving average model to data using the autocorrelation function. And so there's sort of a series of best practices that you can follow to try to construct a time series model. And the first thing is to do a plot of the time series data to get a visual interpretation of whether there's memory in the system. And then you want to plot the autocorrelation function and then the partial autocorrelation function. And so, one of the things we've talked about in the context of time series analysis is getting rid of any non-stationarity, which would be important, right? If we're going to build an autocorrelation model or an autoregressive or moving average model, that is incongruent with this assumption of non-stationarity. So if we see a long-term trend in mean or a long-term trend in variance, we have to get rid of that first before we try to create an autoregressive or moving average model. And we talked about a number of ways to do that. We can linearly detrend the data. We can smooth it. We can take a first difference. All of those are options for trying to get data to be that is non-stationary, to put it into a stationary environment so that we can then estimate an autoregressive or moving average model. So the first thing that could happen if you plot data, if you plot the time series data and then you plot the autocorrelation function and you plot the partial autocorrelation function, and you see no statistically significant autocorrelation or memory in the system at any time lag, then we know that this series is then just is random, right? It's pure white noise. The data are independent, right, and they're identically distributed, so that we can simulate perfectly a process just by characterizing its probability density function and then randomly sampling by a Monte Carlo simulation. So if we do find that the data, after we interpret the original data visually, and then we plot autocorrelation functions and partial autocorrelation functions, and we find that there's memory in the system at any lag, then there's sort of a series, there's a quick and easy guide to picking out the familiar characteristics of certain types of models at different orders. And so, for example, on the left-hand side here, the top figure shows the autocorrelation function. The bottom figure shows the partial autocorrelation function. And so if you have data that is most likely to be, or is best described using an AR1 model, so an autoregressive model of the first order where it's only taking into account one lag at a time, any set of data that's best modeled that way will have an autocorrelation function that looks something like this top left figure, where you see this gradual tapering autocorrelation that goes to zero in some fashion, and the associated partial autocorrelation function with that type of data will show a really big peak in partial autocorrelation at lag 1 and then 0 at every other period. And what that suggests then is that the persistence in autocorrelation that you see in this top left figure is caused by one period to the next a high correlation, right? It's not that the lag between the correlation between period 1 and period 5 is high, right? Or it is high, but it's only high because of period to period persistence, right? So lag 1 persistence, and that's what the partial autocorrelation function suggests, that we could explain most of the variance in this process just by accounting for lag 1 autocorrelation. On the right hand side, we have an AR2 model, right? So data that you can best describe by accounting for memory in the system up to 2 lags, right? And so the autocorrelation function here generally has sort of a sinusoidal feel. You can see that it starts really high, and then it goes low, and then it goes back up high, and then back down. And the associated partial autocorrelation function with that has a really high peak in period 1, and then it goes really low in period 2. So both of these, for the left-hand side and the right-hand side, are generally characteristic of any data that is best described with an AR1 and AR2 model. And we can make fairly similar generalizations about moving average models as well. And this shows the results of this autocorrelation function and partial autocorrelation function for data that's best described using a moving average model of the first order. And remember, to fit the correct order for a moving average model, we're looking just at the autocorrelation function. And we can see here clearly that the highest autocorrelation is for 1, and then at every other lag, the autocorrelation is within these blue bands, and that means it's statistically not significant. And the partial autocorrelation of the function is below. So here is an example of an ARMA model, right? So no differencing, but you have data that's best described with some autoregressive terms and some moving average terms, which means, and the way to interpret that is that the value of some underlying process y in period t is a function of previous values of y. It's also a function of this random noise element wt, but it's also a function of previous innovations of this random noise as well. So there's a lot of memory in the system here. And these are the trickiest because sometimes the order for the autoregressive part and the moving average will not be particularly obvious. And so basically you just have to guess that 1 or 2 terms of each type might be needed, and you see what happens when you estimate the model, and there's various numerical criteria that you use to judge how good of a fit the model is. And in this example, it's a ARMA 1-1 model, which means there's 1 autoregressive lag and 1 moving average lag. So if we find when we plot the autocorrelation function and the partial autocorrelation function that those values do not tail off towards 0, but they stay pretty close to 1 over many lags, that's an indication that the original time series that we're trying to model is not stationary. And so that we haven't done a good job of converting our original data, if necessary, to something that's stationary. And remember, there's a number of ways we can convert or try to convert a non-stationary time series to one that is stationary. You could try to take the first difference, you can remove a linear trend, etc. Now, if you take the first difference and then you plot the autocorrelation function and you find that all autocorrelations are non-significant at every lag, then that is the special class of models called a random walk. And a possible model for a random walk is shown at the bottom here, and it's where what that means is that the value of a process y in period t is only dependent on the process or the value of the process the previous period plus a randomly sampled value from this white noise probability density function wt. And that's would be something that we would describe that has no drift, right? So no gradual linear increase or decrease over time. And overall, it's sort of every possible iteration of this is centered at 0. And it doesn't mean that every simulation is going to be, mean reverting over a long period of time, but there's no gradual linear trend. Now we can add drift into a random walk model, and that's the second equation at the bottom in bold, where you have the value of y in time period t is equal to the value in the previous time period plus some sort of innovation of this random variable wt plus this alpha characteristic, right? So this is a drift, which means over the long period, over the long term, the data is dependent from one period to the next, and it's actually increasing through time as long as alpha is positive. And if it's negative, that means it would be decreasing. So the way we fit these models, remember I sort of described these at one point as multivariate linear regression. And so it's similar, right? The way we fit these models is we're really trying to choose the right coefficients. For an autoregressive model, that means we're trying to find these coefficients b. And for the moving average models, we're trying to find the theta coefficients that overall describe the process the most accurately. And so in general, we're trying to minimize the squared value of all the errors or all the white noise terms in the models. And so I'm not going to go into here how we estimate the parameters via maximum likelihood, but that's built into any sort of model fitting software in MATLAB or any other statistical software. Okay, that's the end of this one. If you're curious about time series modeling, I highly encourage you to look at these links listed here. They're very good in terms of providing some basic information about autoregressive and moving average models.